In order to appreciate how TCP works to combat congestion and overflow problems, we have to look at various instances of transmissions, that is, the realization of window protocol as in static window and dynamic window. When we say static window, what we mean is that the window does not trail or lead. It simply jumps. It is also termed as jumping window. In this module, we shall explore static window and we'll model it. We'd look at its variants such that the effect of the transmission delay, propagation delay, and the object size can be observed. The reference that I chose is again Quiroz and Ross. It is important to understand that the underlying assumptions play a pivotal role in the performance and successful implementation of the protocol. For the static window under consideration here, the assumptions are that there is only one link between the client and the server and it has rate R. The maximum segment size is represented with S in terms of bits. The object size, it could be HTML web page or a figure contained in that, as the object represented in bits O. For the sake of simplicity, we assume that there are no retransmissions because there is no loss and no congestion. And the most important part, we are assuming fixed window of size W. This is the visualization of a simple one-link network connecting the source and the sink, that is, server, sending bits to the client on a channel with bitrate R. If TCP were used to establish a logical connection between the client and the server, handshaking is required. That is what we see here, a three-way handshake. And in the third handshake, the object is also requested. You can see here that the round trip time comprises the sending and receiving of packets. So the RTT is shown in here for the two red lines above. When the request is made, it is one side trip time. So the round trip time is completed when the object starts to get downloaded in the form of multiple segments. The segment transmission time is S divided by R, and the window worth of data is W, which is the window size in segments, multiplied by S divided by R. Since in this situation we see that the segments are being sent back to back, so the acknowledgement is likely to be sent by the client to the server while the transmission of segments is still on. Now this scenario is a unique scenario in which the transmission time is dominating the propagation time. In order to visualize such scenario, and if you were to model it in simulation, the operation has to be seen that the server is not permitted to have more than W unacknowledged outstanding segments. When the server receives request from the client, it sends W segments back to back without expecting acknowledgement for the first one. It sends the window worth of data. When the receiver, that is the client, receives data, it sends the acknowledgement, and when the first acknowledgement is received at the server, this triggers subsequent transmission of segments. So again, the transmission starts from the server end, segment by segment. If we were to model it. We'll say that the server receives acknowledgement for first segment or first window before the complete transmission of the window worth of data. In that case, as I said, the transmission time shown to you here as W times S divided by R is dominating over the round trip time and the transmission time of a single segment. So the overall delay that would be observed shall be 2 round trip times and the complete download of the object.